Eu tô qual a transmissão daqui? Esse do F3, né? É o F3 que eu transmiti?
Good afternoon. I would like to introduce Professor Matthias Hennebuhr. Matthias Hennebuhr studied mathematics, economics, and computer science at Kaiser University in Germany, where he obtained his master's, PhD, and habilitation degree. Currently, he is a professor and head of the Department of Management Science at the Lancaster University Management School in the UK. Since 2002, he has been in the executive committee of the International Society on Multiple Criteria Decision Making, and he is the current president-elect. Matthias Hennebuhr has has about 80 papers published. His contribution in multi-object optimization, and his work has been cited more than 8,000 times. On behalf of Organization of SIGS, I would like to thank you for coming.
Thank you very much for the introduction. I'm very pleased to be here and to give this presentation. I'm not really used to speaking with a microphone. I hope this works. So what I'm doing in my talk is I want to give an overview of some application problems that I've worked on during my career, where I've used multi-objective optimization to make progress on these real-world applications. Now, pick very different topics. So the first one is taken from medicine. I've worked for a long time in the optimization of radiotherapy treatment planning. So I'll talk a little bit about this. The second one is from transportation, and that's a problem that arises in airline crew scheduling. And the third one, manufacturing, the manufacturing of composite materials. Right, so very different topics from completely different areas, but they all have in common that they lead to multi-objective optimization problems. So what I want to illustrate is really the widely different methods that are used in all of these areas, and the benefits that you get by looking at those from a multi-objective optimization point of view. Right, so I start with the medical application, and this is a joke that one of my students, I don't know, he created it or he found it. But what is radiotherapy? Lying on the couch and listening to music, right? So well, not quite. So I'm talking about radiation therapy for the treatment of cancer. All right, how does it work? Well, it's been used for a long time, 50 years or so, or more than 50 years now. And it works because cancer cells lose the ability to reproduce their DNA is damaged. So they're not as good in fixing the damage and healthy cell birth. Right, so you already tumor cells die and you hopefully cure the cancer. The way it's delivered is like what you see in that top picture on the right there. So there's a patient lying on a treatment couch. There's a gantry, this machine that you see, well, it's supposed to illustrate that this thing is rotating around the couch and moves with the unit. And once it's in, you send radiation, all those electrons out, they hit the patient and interact with the body. Right, so modern forms of radiation treatment are called intensity modulated radiotherapy. And intensity modulation is a technique that allows to better focus the radiation on the tumor and therefore achieve a higher dose to the tumor while at the same time protecting better the healthy tissues in the radiation. Of course, this thing is as two contradictory things. You have beneficial effect of the radiation by destroying tumor cells, but of course, if you destroy tumor cells, you can also destroy healthy cells, and that's of course something you don't want. And that's already in the basic setup of radiotherapy. You have the contradictory nature of the goal. So you have the goal of delivering a high dose to the tumor, and at the same time, you have the dose of delivering a low dose, or ideally no radiation, to any healthy organ. Right? So the picture at the bottom shows how the intensity modulation works. This thing is called a multi-leaf collimator. It's essentially a block of metal plates. Each of these metal plates, that's the things that come in from the top and from the bottom layer, can be moved individually, and so you can form a certain shape. You can generate a shape that looks like the tumor, and so you send the radiation through the metal leaves, block the radiation, and you only irradiate the tumor. In addition, you can superimpose several of these shapes on top of each other, and that gives the modulation. So essentially, instead of just sending the same intensity of radiation across the whole radiation field, you can now subdivide this into the leaves, and each leaf can stop in a certain number of leaves. Basically, subdivide this radiation field and individually decide what the intensity of radiation for each of these little grid places is. That's what intensity modulation means. So, there is on the right. Obviously, we have a scan of a brain, right? And you see in the center of the brain, the blue area, that's the brain stem. So clearly, you don't want to radiate that thing because that's vital. The red area next to it, that's the brain tumor, so you want to irradiate the tumor. And you have highlighted the eyes, you don't want to do that. And the colored lines that you see there are called isodose curves, so they are level curves of the tumor. Of course, the highest number of the tumor is, and then as you go further out, the dose of the radiation goes down. So this is what you want to design, right? So you want to have a dose distribution that concentrates the radiation dose to the tumor and skips the healthy organs surrounding it. How do you do this? Well, now go to the left of the picture. This is what you get when you digitize the radiation field. So this is the radiation field, completely open. With the multi-leaf collimator, you get this subdivision into grids. Each of these for which you can decide what's the intensity of radiation. So the white is and the black would say very high radiation, and the gray is radiation Right? So what we have to, now this is the decision variable, right? So we can decide what these colors are in order to get what we, those distribution that we put on the right. So this is the problem, right? How do we decide what this map looks like? It's also called an intensity map or fluent map, and that's our task. So, well, next we have to derive a mathematical model of this direction. So basically what you see on the top, now I'm reducing this by one dimension, so this grid is of course two-dimensional. If we just think of one row of this grid, we'll have these beam elements. So that's one row in this, one column or one row in the multi-leaf collimator that I showed you before. Right? So we call these beam elements or pixels for short. And the intensity of those basically means for how long do we irradiate, because the linear accelerator that generates the radiation has a certain energy, and that is fixed. So we can only decide how long we irradiate each of these pixels. Now, radiation comes out of the linear accelerator, hits the patient. So what we do here is we discretize the patient as well into 3D blocks, basically, which we call voxels for volume elements. And we pick one point in each of these voxels where we measure the radiation dose, and that represents the radiation dose in that whole voxel. So we have some notation there. So Aij is the dose delivered to a certain voxel by a certain pixel if we irradiate for 1 second, say, or 1 unit. Xj is the intensity or the time for which we switch on the radiation in each of these pixels. So that's our decision variables. And Vi is the dose that delivered to the voxel. Now, these are related in a very simple linear relationship. E equals A times X. Okay, that's very nice. Now, so this tells us how we get the dose out of the radiation intensity. And now we need to form an optimization model that makes use of a linear relationship. So how does that work? Well, if you look in the medical physics literature, there are lots and lots of models that do that. You can easily find 10 or 15 or 20 different ones. Different oncologists, different medical physicists have a different opinion on how that's supposed to be working. I'm going to present you a very simple one, which is not one that's really used in practice, but just to illustrate how that works. Okay, so basically what we always have is a prescription dose. So we want to irradiate a tumor with a certain dose. For example, take a prostate cancer, and the general consensus is that we should irradiate the prostate with a dose of 74 gray, for example. So that's the target. At the same time, for all the critical structures, in the case of the prostate cancer, that would be the bladder and the rectum, which are right next to the prostate and therefore needs to be protected. We have an upper bound. So we say the rectum should not receive more than 50 gray, for example, and the bladder should not receive more than whatever, I don't know the number. Right. So basically now we have goals to achieve. So I've written this down, and remember I've said dose equals A times X, so the T is now gone, I'm always writing X. And the subscript there, the T refers to tumor, so that's in the A matrix, only those rows that correspond to tumor voxels, so they tell me what the dose is in each point in the tumor. So this ATX, I want to be greater or equal than the tumor lower bound, the 74 gray. Okay, I also have an upper bound, and the upper bound is to avoid what is called necrosis, which arises when you have too many dead cells in the body. So the body can't cope with the dead cells, we don't want to do that. It has other side effects. For the critical structures, that's what C means, and the normal tissue, that's everything else. There's obviously an upper bound. You don't want to go beyond that. Now, if you formulate a problem like this, you just have inequality constraints, but there's no objective, right? So if you find an X that satisfies this constraint, that's great, right? And you have a plan. However, if you set these plans, you don't know if that's even feasible, right? If you set the tumor lower bound too high and the critical structure upper bound too low, then maybe there isn't any plan. But that doesn't work. You can't solve it as inequality constraints. So what we say is we elasticize this. So we'd like to have the tumor dose greater than the lower bound, but if that's not possible, we're willing to give up something. So that's the minus alpha. For the upper bounds, it's the opposite way. If it's not possible to meet them, well, let's go a little bit beyond and see how much that is. Obviously, these deviations from the ideal should be as small as possible. So we minimize the deviation from the tumor lower bound alpha, the deviation from the critical structure upper bound, gamma and delta, beta in the middle, and gamma the deviation from the normal tissue upper bound. Okay, we want these to be as small as possible. So here, 3 objectives, very simple one, and a linear programming model. Okay, and we have in the model implicitly trade-off between achieving tumor control and avoiding complications in the normal tissues. Right. So that's the model. Now I'm going to the math. Okay, so that's the model of my decision-making problem, and now I need to do some math to solve that problem. So in a multi-objective linear program, which we have here, we have, for example, the horizontal axis represents the tumor deviation, and the vertical axis represents the critical structure deviation from the target domes. Okay, it's a linear program, so everything is a nice polyhedral set like there. So Y, this diamond shape, is a set of all feasible deviations that we can achieve by all possible plans that we make. And P is just saying, okay, anything worse than the minimum we don't care, so whatever happens up there is of no relevance to us. Now we need to find the lower boundary of that set. Okay, so how do we go about this? So what we can do is we easily compute the lowest possible deviation in both of the objectives, which is 0, of course, if we do not irradiate and we do not violate the upper bounds for the critical structures. If we irradiate just a lot, we kill the tumor and the patient too. Theoretically, it's possible, right? So 0. We take this point, which we have, and we know that everything is feasible, must be to the right and above from that point, from that blue dot down there. Right? So, and now the method just takes a line that goes out from this point. It must intersect the boundary somewhere. We find out where that intersection is and calculate the supporting hyperplane that cuts off that point. So in the process, we find part of the boundary limit. Okay, and we create 2 new corner points, the blue dots, and we iterate the process. So in this case, it's of course a simple example. After the second iteration, we're done. All right, so we now have found the boundary, which is the some people call the Pareto frontier or the non-dominated set. Yeah, we've solved the problem. So we have all the possible trade-offs between tumor control and protection of normal tissue. Right. So we solved the problem. What do we tell our medical physicists to do now? Well, still infinitely many options, right? So actually, from a practical point of view, we know what the trade-offs are. but we don't have a plan yet. So to do that, we need a little bit more of theory. So for this multi-objective linear program with the minimization problem, there's also something called a dual. Right? So just like in linear programming, there's always a primal and a dual. One is a minimization problem, one is a maximization problem, and their objectives are the same. The optimal objective values are the same. We can do a similar theory for multi-objective linear programming. It's also multi-objective dual optimization problem, which in this case would be maximization. Okay, it's called geometric duality because it has a lot to do with the theory of polyhedra in geometry. And the algorithm that I just shown you is called an outer approximation algorithm. This is because we always have a set that approximates the feasible set from the outside. Okay? This algorithm, because of the relationship between the primal and the dual, also does something with the dual NP, and it becomes an inner approximation of the dual problem. Right? And we can also apply an outer approximation algorithm for the dual problem, and that becomes an inner approximation algorithm for the primal problem. So now we have two things, so we can always approximate from the outside and from the inside. And what that means is we have a quality guarantee on how far away from the optimal solutions we are. Okay? And we can stop the algorithm at any point and we will know exactly how good or how bad the solution that we found there is. Okay, so this works like this. So I'll just show you, this is an example of a primal problem, and this is a picture of the corresponding dual problem. And I show you how I apply the algorithm to both of these problems that we have solved. So here's the initial, same picture as the sheet, it's a rectangle. And as we go ahead, you see how on both sides something happens, and it's an outer approximation here and an inner approximation there, but at the end, we have completely. Okay, so it's better, but still doesn't give us a plan, right? So we've done this with real tumor chains, and you recognize this. It's the same brain tumor chains from the picture at the beginning. There's some data of how big that problem is, and we let the algorithm run with different errors. As I said, we have a guarantee of how good the solution is when we stop early. So this is what this looks like. So we have the curves now because we have three objective functions that tell us the trade-off between all the three objectives. Right. But still no plan. Okay, so from a practical point of view, it's actually not very useful to say, well, here's a definite number of plans, one. But how does the decision maker, how does the radiotherapist now choose a plan? I've just told him the program is as hard as when we started, right? So as a consultant, I have failed. So maybe we should do something else. And we should give him a collection of plans for which we know how good they are and how different they are. Then there's only a finite set of plans, and then it's much easier to choose from 5 plans than from many, right? So this is how this works. So we first construct something like this. Here's the set Y again. You find that point up there, which is the worst value over the previous set. You construct this triangle around the feasible set, which for which we also need this point. And this point we find by just optimizing the sum of all the objective functions. We can construct this triangle. Know how to find the corner point. So we have this triangle equilateral. Then we put a number of points on this hypotenuse of a triangle like this, and we project these points towards the set. Sometimes this will result in no point. This always can be done by solving a linear program. And in the case up here, it just means that here, linear program is infeasible, so there's no solution. And sometimes it hits the non-dominating set. In this case, we found a plan that has now a specific trade-off between the objective functions. So what we can do now is say to the decision maker, we've computed 5 plans. They all have a particular trade-off between the objectives, and they're all different. And we know how different they are because we can prove what the quality is. Again, so it's a much better approach. Now we have a finite number of plans, and the decision maker needs to pick one. For example, like this. So here's our case again, and these are the points on that surface that we've computed. Okay, so these are now the feasible plans. How do we? And now we have to help the decision maker choose one. So we've done this. So in the first instance, the system generates a plan where all of the objectives are as equal as possible. And the reason for that is we don't know anything about the preferences, so we just say, well, let's look for a plan where the deviation from the tumor goal and the open goal is pretty much the same. It's this one. Okay, remember that these numbers mean the deviation from the upper bounds and from the lower bounds. The 36 seems high, but that's because we've set the goal for the normal tissue to 0. We don't want to irradiate it at all. Okay, now this, well, then I might think the 3.8 is a bit high. So there is some point in the tumor where we almost draw gray below the actual goals that we wanted to deliver. So we would like to improve that. So we can now tell the system, now find us and only set of plans with one where the first objective is better. Right? Very easy to do because we have this database of plans, we just need to pick it, and this is the result. Okay. It has done what it was supposed to do. Result for the tumor is better, but well, there's a cost of it because it's conflicting objectives, so the result for the critical structure has gone up. And if that's too much, I can say, okay, we like to keep the first one, but reduce the second now. Okay, it doesn't work. All right, so the second has indeed improved because the minus means we've gone -1 grain above the upper bound. That means actually we're always below the lower bound. So there's a brilliant result, but the tumor now is even worse than the first one. So that's probably no good. Another iteration. Okay, there was an option that keeps the minus in the second objectives and reduces what the first objective. So this is certainly much better than the previous one. And another goal, let's see if this works. And we have a system that can help the decision making. So compare this to current practice. At the moment, what planning systems do is they just take the objectives, form a weighted sum, optimize. If that result is no good, what do? The only influence on the plan you have is changing the weights. So you make an educated guess on how you should change the weights in order to get a plan that you like. It may work or it may not work. So there's a trial and error process. So with the objective approach, we could actually explicitly model conflicting objectives and model the trade-offs and therefore make use of them. And in addition, what we got is a better process for the planning. That was never part of the model. That just happened because we used the multi-objective perspective to look at the plans, right? So there is some benefits that you get delivered essentially for free. Right. Completely different subject now. I talk about transportation. Are there any questions on the medical application, by the way? It's best to ask now. Okay. So, transport. Yeah. Yes, that's part of the information that is presented to the planner. So what we see is not just showing these pictures. I haven't explained what they mean, but this is on the left is dose distribution picture, and on the right is what is called a dose volume histogram. That shows how much of a particular volume receives how much dose. So you want, so the red line is the tumor, and what you want there is you want all of the volume. So that's the one on the horizontal axis receives the prescription dose. So that line looks rectangular in the ideal case, and the other ones are the opposite. You don't want any of the volume receiving any dose. They look rectangular, but the opposite way. In addition, there's a lot of information that planning systems also tell the patient, tell the planner patient. Okay, so that would include also where the dose is and where the hotspots are. I haven't shown them. Right. So transportation. At the time I did this work, there was this piece of news on BBC about an airline who had a big problem because they had planes and pilots and passengers all over Europe, but none of them were in the place they should have been at that time. So what happened? Did they need optimization? Well, actually, the problem happened because they used optimization. And I'm trying to explain that in the course of the next slide. So what is airline crew scheduling? The way an airline plans is first they design where they fly. So they design their flight schedule. Then they allocate aircraft to that flight. Now know which aircraft is operating which flights, and of course that's sort of a collection of round trips from the airline base and eventually come. Right, so once you have time to the flights, you have to decide which pilot, which cabin crew operate each of the flights in their schedule. How do you do that? As a medical model that's commonly used there, is first you construct theory all of the possible variants. That means all of the sequences of flights that a particular crew member can operate. And that's just a vector of 0 and 1. So you have the vector is as long as there is the number of flights, and you put a 0 if the crew member does not operate that flight, and one if it does. And there are, of course, constraints on what these can do. So between the flights, there has to be a certain minimum sit time where they have to wait before they can fly again. They have to return back to home at the end of the pairing and things like that. But essentially, it's just a contraction of a lot of 0, 1 vectors to tell you what's possible. Now you solve a set partitioning problem. Because in fact, of course, for each flight, you need exactly one pilot. Right? So now you make constraints, which they make
Individual being achieved, not the child. Sim. Eu vou